All right, hi everyone. Let's solve the first example in chapter 6. It is the example given on page 7. Let's read the question first. So, example. Using the previous assumption in an Ohm's law table, find the current through each resistor. So basically, we're going to be using the assumption that there is no voltage drop in each wire and Ohm's law to solve the current through each of these resistors. So on the question itself, the example, there is this diagram. Now note it is a rather complex circuit, especially at this point we did not consider any of the rule and concept needed to solve complex circuit. However, you will see that just with Ohm's law and our simple assumption that we made previously, we can solve that problem. All right. Now note there's three power supply, this one over here, and this one over here. So this one is 5 volt, 2 volt, 8 volt. There's 3 resistor. By the way, there's no notation for the resistor, so you can choose whichever one you want. So I decided that the 3 ohm over here is going to be our R1, the 2 ohm over here is going to be our R2, and the 4 ohm over here is going to be our R3. Now, in the question, we are asked to create a Ohm's law table. So Ohm's law link the current resistance to the voltage drop on each resistor. Now, basically, Ohm's law table is a table where the row is the resistance. So here we have R1, R2, R3, and the column are the resistance of each individual resistance, the current through each individual resistance, and the voltage drop through each individual resistance. So let's add a delta over here just to say that it's a change in potential. When a charge goes through a resistance, it loses some energy in the form of a drop in voltage. Now, we already know the value of each resistance. It is given. So this R1 is 3, R2 is 2, R3 is 4. So 3, 2, 4, we already got that one. Once we get the voltage drop, we can find the current here. And the way we're going to proceed to find the voltage drop is to look at the voltage on each wire. Now here, one symbol that I did not talk about is the ground over here. So the ground tells us that this section, the wire connecting this section, is at 0 volt, and my marker had to die right now. So if we measure the voltage at all points with respect to the ground here, well, we get a 0. Now, let's have a look at the 3 other wire that we have in this circuit. We have another wire over here, another over here, and a final one over here. So, the battery over here is like a pump, giving the charge an extra 5 volt of energy. What that means is, the wire over here, this one, and I'm gonna use pink, so pink over here, this one is at 5 volt, this one is at 0, the charge gets a boost of 5 volt of energy, so this wire is at 5 volt, all right. Now, this one over here, we cannot figure out the voltage from here. However, using the same logic, we can go from 0 and the charge will get a boost of 8 volt on that side, which means this one is 8 volt. Now we're going to follow the exact same logic for the final wire. Note, we don't know the voltage on the lower side, on the negative side of the power supply, but we do know that this wire is 8 volt and this side has to be 2 volt higher than that side because of the power supply. Well, 8 minus 2, it's 6 volt. We got 6 volt over here. Now, at this point, we know the voltage on each wire with respect to the ground. What that means is we can find the voltage drop on each resistance. Let's look at R1. We got 8 volt. We got 5 volt over here. The voltage drop here is 3 volt. So 3 volt over here. Now note, the current over here will always go from the highest voltage to the lowest. So the current is flowing in that direction, from the 8 volt to the 5 volt. Sometimes we may write the polarity of a resistor. So on this side, the voltage is higher. On that side, the voltage is lower. Now, by the way, when I say polarity, it just means the direction in which the current flow in this circuit. Resistor itself does not have any polarity, but when there is a voltage applied, the current will flow in a certain direction depending on the circuit. In this case, it's flowing to the right. Now, we know that the current multiplied by the resistance is equal to the voltage. So R multiplied by the current is equal to the voltage drop. Well, that means we just found the current. It is 1 ampere. All right. Now let's repeat the same process for R2. Well, R2 over here is 8 volt on one side, 6 volt on another side. So this will be a positive side, negative side. The charge will be flowing upward, and it's a difference in potential of 2 volt. So we got 2 volt over here, same logic as the previous one. We got a current of 1 ampere going through R2. Okay, one last one, it is R3. So in the case of R3, we have 0 volt over here connected to the ground, and we've got 6 volt over here, so there's a drop of 6 volt. So the resistance multiplied by the current has to equal the voltage, so the current is 1.5 ampere. All right, so we were easily able to solve the current in each resistor using simple assumption. Now, obviously, in this chapter, we are going to cover many circuits where it is not possible right away to know the voltage on each wire. But most of the time, you will be able to figure it out on some of the wire. Use these tricks to get some information in order to advance while you're trying to solve the problem, okay? In this chapter, it is true in all of physics. It's a matter of obtaining information and what can you do with this information. And I think this chapter really highlights that fact. We are going to advance and get an extra piece of information and another extra piece of information. Each step is not too complicated, but we have many steps to do. All right. So in the next video, we're going to start tackling series circuit, parallel circuit, mixed circuit, and eventually lead up to more complex circuit using Kirchhoff's law. All right. So see you in the next video.